Welcome, everyone. Um, my name is Casey Wang, and I'm a co-PI for the Fabric project. Thanks to everyone for joining us today for our sixth Stitching Together Innovation with Fabric Users webinar featuring Zilinghan Li, Ravi Maduri, and Zilinghan today. Before we begin, I'd like to share a few housekeeping items. If we can go to the next slide. The webinar will include a live question and answer session following the presentation. And you will note that the Zoom chat feature has been disabled. If at any point you want to ask a question, please just go ahead and type into the Q&A box on the bottom of your screen, and we will answer all the questions during the Q&A session. Finally, this webinar is being recorded, and we'll be sharing that with all the registrants. Next slide, please. Today, we're joined by three presenters altogether. So our presenter, Zilinghan Li, and his teammates, Ravi Maduri and Zilinghan. I'll briefly introduce them. Zilinghan Li is a machine learning engineer in the Data Science Learning Division at Argonne National Laboratory. He holds a Bachelor of Science in Computer Engineering from Zhejiang University, China, and a Master of Science in Computer Science from the University of Illinois at Urbana-Champaign. He is the lead developer of the Advanced Privacy-Preserving Federated Learning Framework, and he is also deeply engaged in developing AI models for biomedical and scientific applications, advancing the frontiers of data-driven discovery. Next, Ravi Maduri. Ravi is a senior computer scientist focused on applying AI and high-performance computing to accelerating scientific discovery process. His research interests are in building sustainable, scalable services for science, reproducible research, large-scale data management, analysis using HPC and AI. He leads the Palisade X project that is developing privacy-preserving federated learning framework to build robust, trustworthy AI models. He co-leads the MVP Champion project, which is a collaboration between VA and DOE, and develops methods to perform large-scale genetic data analysis using DOE's high-performance computing capabilities. Additionally, Ravi was one of three key contributors to the National Institutes of Health 100 million cancer biomedical informatics grid. It's called CA-BIG, which linked 60 NIH-funded cancer centers and clinical sites engaged in cancer research. For his efforts in project management, tool development, and collaboration, Ravi received several outstanding achievement awards from NIH. For his work on Cancer Moonshot Project, he received the Department of Energy Secretary Award in 2017. Lastly, Zilinghan is a dedicated visiting research associate at Argonne National Laboratory and a graduate student at the University of Illinois at Urbana-Champaign, specializing in AI and HPC, with expertise in training large language models, federated learning, and optimization for inference. Zay has contributed to cutting-edge projects enhancing medical diagnostics and scientific research. Zay is passionate about leveraging innovative technologies to solve complex challenges and drive advancements in computational efficiency. Now, I will pass on to Zilinghan to begin the presentation.
Thank you, Casey, for the introduction, and hello, everyone. My name is Zilinghan Li, and I will primarily present this webinar. It's really a great honor to co-present with Zilinghan and Ravi Maduri. So basically, in this webinar, we will be talking about when federated learning meets fabric. And before we dive deep into this topic, let's first talk about what are the motivations for using federated learning. So as we might aware of that, we have already entered an area of artificial intelligence. We have seen many artificial intelligence that really change our life. For example, like several years ago, the face recognition models have been deployed in many modern mobile phones. And nowadays, ChatGPT is very well known, and it really changed the work style for many people. And AI models are also widely used in many domains, in scientific domain, in biomedicine, in finance, in sports, in entertainment, in advertisement. So it is used almost everywhere. And one of the key to the success of those AI models is the sufficient amount of high quality data. So we say sufficient data is essential to training high quality and generalized AI models. But actually, in practice or in real world, the data within a single data silo are usually limited and biased. By limited, we say, yeah, we don't have you know, like a large amount of data for us to train a good model. And for bias, for example, we can think, the data within a single data silo usually just represent the population just near of the nearby geographic area, and it may not represent the general population. And the data are very likely to, distribute heterogeneously among various data silos. So what people usually want to do is that how about let's just collect this data from distributed data silos. For example, when people are training ChatGPT, they use data from archive, from bioarchive, from textbooks, from the web, from the internet, and they also use from social media. They collect data from different sources to make sure that the data are generalized and well represent the general corpus. And in training other AI models, people are also wanting to collect data from multiple sources so that they can get a more robust and generalized model. However, in certain sensitive domains, such as finance and biomedicine, collecting such data into a central location is very, very hard, if not impossible, because there are a lot of privacy concerns, like the patient sensitive information are not allowed to share outside the hospital. And within this scenario, we just make the claim that fed learning could be one of the very promising solutions which can enable the training of a more generalized machine learning model without direct data sharing, and how it works. So in this figure, we briefly show the workflow of federated learning. So federated learning is actually a distributed machine learning paradigm, and it has multiple clients. As you can see in this figure, we have 4 clients, and each client has its own computing resources, as well as some private local data, either reside directly on the resources, or it may, securely stored on a private cloud, so that only the client themselves can get access to those private data. So 2 things, computing resources and private local data. So in addition to those clients, there's also a central orchestration server, which orchestrates the federated learning process. And how it orchestrates? So in federated learning, each client will train a local model using their private local dataset, and then share the model parameters to the server for aggregation. So by aggregation, people can simply understand that as a weighted average of the model parameters shared by different clients. So in this case, the aggregated model kind of implicitly leverages data from multiple clients to obtain a more generalized model without directly sharing the data, the private data reside on each client. So in this case, without direct data sharing, we can leverage their data and get a more generalized model. So due to the distributed nature of federated learning, there are various challenges in federated learning. So the first one is the heterogeneity of the data. So as we mentioned, one client data may be biased, and they may just represent, the population that of the nearby area. So the data of each client can be very heterogeneous. For example, in the first plot, we can see that the distribution of the intensity of different clients are completely different. Or when you reduce the dimension of the client's local data, you can see that they can form completely different clusters. So the data are heterogeneous. With that, when different clients are training machine learning model using this heterogeneous client, they may have different local objectives, and they may diverge into different area, and such divergence may impact the performance of the aggregated global model. So that is one of the key challenges in federated learning. Another challenge is that the compute of each client can also be heterogeneous. As we mentioned before, in federated learning, each client has its own computing resources, and these resources can be completely heterogeneous. Some may use on-premise supercomputers or HPC or even some other server types, where some other clients may have their computer resources on cloud using Amazon Web Services or Google Cloud. These computing machines may have different operating systems, different hardware architectures, and more importantly, they may have different computing power, so that when you give almost the same amount of training tasks to different clients, they may complete that in completely different amount of time. And in such case, when everything happens synchronously, then the clients with more powerful machines will be waiting for the clients with less powerful machine, and this will cause a lot of resource wastage and making the training very inefficient. This is the second challenge of federated learning. And the third client is that sometimes the clients can be, malicious. They may use some, fake training data, or they may just upload random model parameters to the server to attack the training process. Whenever like a poison model parameter is sent to the server and used during the aggregation process, then the performance of the global aggregated model will degrade a lot. So this is the third challenge, malicious attack from certain clients. And the fourth challenge is data reconstruction. So in federated learning, as we mentioned, no data are directly shared between the server and clients. Only the model parameters are shared. However, there are some studies which has already shown that only using the parameters shared between the server and the clients can be used to reconstruct the original training data. So in this plot, you can see on the left-hand side, it is the original training image of a chest X-ray image. And on the right-hand side, it is a reconstructed image just using the model parameters sent between the server and clients. And this reconstruction can clearly show that at least it shows this is the chest X-ray image. And sometimes we want to avoid that. We don't want such data reconstruction to happen because it may also leak some privacy information of the training data, and it may cause a lot of security concerns. And finally, as federated learning is distributed, so the setup for and the setup for the coordination between different clients can be a tedious process. And with those challenges, our framework, APPFL, the Advanced Privacy Preserving Federated Learning Framework, is our framework-wide solutions to all those challenges. And then let me talk about how we really resolve those challenges within our framework. So for heterogeneous data, FO framework integrates a bunch of advanced aggregation strategies, which basically use some server-side optimizations to address the heterogeneous data problem, to avoid the global model to drift, to avoid each local model to drift away too much from the global model. For the heterogeneous compute, in addition to the general synchronized federated learning algorithms, FO also integrates many advanced asynchronous scheduling algorithms, which improves the resource utilization of each client. For malicious attack, FO supports robust authentication so that the user can know that who they are exactly collaborating with by just verifying their institution emails. So they can invite trusted collaborators using their institution email to form a very secure federation using our robust authentication features so that it can reduce the risk of malicious attack. For data reconstruction, FO integrates several differential privacy and privacy enhancing techniques, which basically either add noise to the model parameters exchanged between the server and clients, or encrypt the model parameters to make the data reconstruction much harder for the attackers. To simplify, the setup procedure, AppFlow have a very simple experiment configuration manner, which makes launching federated learning very easy for the first-time user. So yeah, here's a summary of our AppFlow framework. So AppFlow is an open source federated learning framework which supports comprehensive solutions for various federated learning challenges. And here is the manuscript, which describes the latest feature of our AppFlow framework, the overview of the framework design, different kind of challenges that the framework could address, and the evaluation of different capabilities of the framework. And it also provides some additional case studies which show that the AppFlow framework can be used for various advanced usage. And AppFlow is fully open source on GitHub, and we always welcome issues and contributors from the community who have interest in federated learning. And AppFlow is also well documented at APPFL.ai. If you are interested, you can directly type APPFL.ai in your browser, and it contains very detailed tutorials starting from how to install AppFlow on your computer, how to launch experiments easily, and it also contains some advanced developer guides if you are interested in contributing to our framework. And finally, another interesting feature of AppFlow is that AppFlow also provides a service platform available at service.appfl.ai. So it is fully based on AppFlow, and it is designed for domain scientists who don't really have much information, or have much expertise in computer science. This platform is built for simplifying the procedure to launch federated learning experiment with user-friendly dashboard and experiment launching forms. So it will also help the domain scientists to launch federated learning experiment automatically and generate comprehensive reports after each experiment for getting more insights of the federated learning. So if you are interested, also check it out. Okay, now let's talk about the integration, like the collaboration between AppFlow and the Fabric testbed. So AppFlow choose Fabric as the testbed. And why we do that? What are the benefits that are provided by the Fabric testbed? The first benefit is that Fabric could easily offer us a heterogeneous and geographically distributed testbed for testing and benchmarking distributed computing applications. As we mentioned in the challenge part, computational heterogeneity is one of the key challenges, as well as it is one of the key features of federated learning. So we have to, whenever we run federated learning experiments, or when we are develop algorithm for federated learning, we should take that into account to simulate an experiment where different clients have heterogeneous computing resources with different computing power. So without Fabric, this can be a tedious process. You have to, find the different laptops or different servers at different places, geographically different places. And that is very hard to do that. But with Fabric, we can get all these heterogeneous resources easily within a single Jupyter notebook. We can allocate as many heterogeneous nodes as we want easily using Fabric. And with that, we can, benchmarking, a lot of federated learning experiment under a heterogeneous environment. A second benefit provided by Fabric is that it could help us to explore the role of network in training models across geographically distributed sites. And this is especially important when we are working a very large data set at each location. We can see how the network impact the efficiency of federated learning when dealing with large data sets. And the third benefit provided by Fabric is that it supports inbound connection. So what does this mean? So unlike many supercomputers, such as Polaris at Argonne National Laboratory, the Fabric supports server, which allows inbound connection to the clients. So basically, for a supercomputer, it usually closes the port for inbound connection from outside the world. So it cannot work as a server. And before using Fabric, we have to go to some cloud providers such as AWS to launch a server so that all the clients can talk to the server. But Fabric is different. In Fabric, you can launch several nodes, and this node, like say 3 nodes, and these 3 nodes can talk to each other directly with inbound connections. And more importantly, outside the Fabric allocated node, you can also talk to the clients by using some credentials setups. So this makes Fabric very ideal for hosting federated learning server. And also, with the credentials, outside world can also connect to the server. This also makes things secure as well. And the fourth benefit of Fabric is that it provides advanced tools for measuring the latency and monitoring the resource utilization throughout the federated learning process. So we can monitor what is the latency, during the communication, how many resources are utilized at different client or different client nodes, whether the computing are fully utilized or not, whether the network is fully utilized or not. So with Fabric, we can do that as well. And the fifth benefit, and it is also one of the most important benefits, is that Fabric allows seamless connection to external facilities for additional computing resources. For example, Fabric now can connect to Chameleon facility ports, which can help users to get access to more computing resources with more GPUs, so that people can use Fabric to do more compute intensive applications. So with these benefits, what kind of experiments can be enabled by the Fabric testbed, related to federated learning? So the first kind of experiment that Fabric can enable is that it could help us to benchmark the communication latency of various communication methods and protocols used in federated learning. Second, it could help us to measure the training efficiency of several synchronous and asynchronous algorithms on distributed and heterogeneous machines. So let me add more details here. So from this plot that I show, this is one of the plots we have in our in one of our asynchronous algorithms that we propose to address computational heterogeneity problem. So in this plot, at that time we don't know Fabric, and we don't use Fabric to do the experiment. And we have to simulate a heterogeneous computing environment by having each client, to sleep for some time to simulate that heterogeneity. This is very tedious, and it cannot represent the real world heterogeneity, to be honest. But with Fabric, we can easily allocate the real world distributed and heterogeneous machines, and that could be a very ideal test bed for benchmarking various synchronous and asynchronous algorithms in terms of their communication, in terms of like the training efficiency. And finally, Fabric can also help us to evaluate the scalability of the framework, of the APPFL framework, as the number of client grows. So now, after talking about the benefits of Fabric and the kind of experiments of Fabric, now we will plan to give a very short demo, which kind of give a prototype of running APPFL on the Fabric testbed. And here's the setup for this demo. So the first step is that we need to set up and customize the configuration for the Fabric platform to ensure smooth execution of the task. And for the first step, people just need to follow the Fabric's tutorial Jupyter notebook. It is well written, and you just need to follow the same step to do it. And after setting up the Fabric environment, it is time to allocate the resource and provision nodes. So in this case, we allocate one node, which act as the Federated Learning server, and two more nodes, which work as the Federated Learning clients. And these two clients will communicate to the server to train a machine learning model in a Federated Learning manner. And after allocating the resources, then we will securely connect to the three remote node using SSH for seamless interaction and experiment configuration. After SSH to those nodes, we will install the APPFL framework on these three nodes and then modify the configuration for running the experiment. And finally, we will launch the experiment and continuously monitor the performance to ensure the accuracy and efficiency. So now I will give the demo. We record a short video for this demo, and I will show it now.
Before starting the project, we first set the project ID and generate the configuration. Once generated, we can display the configuration for review. This process creates essential files like sshconfig. Next, we validate the generated configuration to ensure everything is in order. If all checks pass, we save the configuration. Finally, we can see the saved files, including sshconfig, directly in the Fabric config. This workflow ensures everything is ready to proceed smoothly.
So this notebook is available at the Fabric tutorial page, and we just modified the project ID. So if you want to reproduce it, you just need to go to that Jupyter notebook, and you just need to change to your project ID, and you can configure the Fabric.
After completing the configuration setup, we can start our experiment. First, we import the needed libraries and the config. Once imported, the configuration details are displayed. To simulate multi-site communications, we randomly select 3 sites for node creation, with each site hosting one node. This step may take some time. After securing the sites, we create a slice to manage the nodes and set up one Ubuntu node at each site. The setup process also requires some time to complete. Once the setup is done, all slice, node, and network information is displayed, showing their active status.
As you can see here, we allocate 3 nodes, 1 for the server and 2 for the clients.
Before proceeding with the experiment, we test connectivity by pinging between nodes to ensure everything works smoothly. If all is well, we open terminals, connect to the nodes via SSH, and set up APPFL.
We're copying the SSH command from the Fabric generated output.
After completing the APPFL setup, we run the Federated Learning experiment on the NIST dataset using gRPC as the communication protocol.
So in the first terminal, we launch a server. And in the other 2 terminals, we launch 2 clients which connect to the server.
Now you can see the transfer between nodes starting.
Yeah, so now the server can receive the different kind of requests required to do the federated learning. You can also see some logs which can reflect the training process, such as the loss and accuracy throughout the training process. On the client side, you can also monitor the validation loss and accuracy during the training process for this certain client.
Finally, after completing the experiment, remember to delete the slice to free up resources.
Yep.
Thanks for watching.
So this concludes a very simple demo, which gives a prototype of running federated learning using the APPFL framework on the Fabric
Before
test
starting
lab.
the project,
So here are some receipts for this demo, for this short demo. So the first link contains the setup notebook for Fabric, which allocates 3 nodes, one for the server and 2 for the clients. If you are interested in reproducing this demonstration, just go to this notebook to set up, to allocate the resources. And in terms of like how you can install APPFL on those nodes and how you can launch the experiment launching script for both the server and clients, we also provide the experiment setup and launching scripts in this link. And if you are interested, you can go to this link and find out how to do that. Okay, so after the demo, now it's time for us to envision what are the future work and future paths for us in terms of the collaboration between APPFL and Fabric. So the first one is the Chameleon integration. As we mentioned that Fabric can be connected to Chameleon facility port to get access to more powerful machines. We will be doing that so that we can use Fabric to run and test more computational intensive experiments. And the second future work is that we would like to leverage Fabric's configurable network and seamless node connectivity to optimize federated learning for large-scale climate data so that we can avoid transferring large amount of climate data and improve the model performance. So for more information about this application, APPFL and Fabric work together to write a user story, which contains more details of this future work. If you are interested in that, feel free to check it out. And that's all for the presentation, and thank you so much.
Well, thank you very much, Zilinghan. So now we will enter the Q&A session. So if we can, yep, update the screen. We'll begin with questions that are submitted during the presentation. The first one I see in the slides, you mentioned several challenges related to federated learning. How does the APPFL framework tackle those challenges?
Yeah, so actually, APPFL is a framework. It is not a certain algorithm towards a certain challenge. So how it address different challenges is that during the framework design, we have those challenges in mind. So we first do, some literature review to think what are various challenges, reside in federated learning. This is the first step we do. And then during the framework design, during the how we connect different components, we have these challenges in our mind so that we design certain components for addressing those challenges. So with that, we have a framework which have necessary components to address different challenges. And the last step is that within different components, we integrate a lot of existing state-of-the-art challenge resource solutions to those challenges. For example, in computation heterogeneity, we mentioned like different clients have different machines with different computing power. We specifically design a scheduler component, which does not exist in many existing federated learning framework. So that scheduling component can integrate a lot of advanced asynchronous scheduling algorithm, which better utilize and better orchestrate the training process to improve the resource utilization. And for like some security concern, we also have like privacy component which integrates differential privacy and privacy enhancing techniques to address those challenges. Also, we have authentication components as well. So basically, to summarize, how we address those challenges is that we have a good framework design and we have comprehensive solutions in different components of the framework.
Thank you. The next question. In federated learning, data is usually private and confidential. How can people move private data to Fabric resources?
Yeah, actually, this is a very good question. So in Fabric, what we usually want to do is that we don't want to do real experiment on private data because usually like collaborators don't want to move data to Fabric. But actually, we want to use Fabric as a test bed to first test and prototype federated learning using some like either synthetic data is fine to just test the end-to-end workflow and understand what are the challenges for federated learning or what we need to modify and so on. Like just make the workflow run through end to end. And then with that, on Fabric, we can then launching real world federated learning experiment on the client's own computing resources using the private data that they cannot be shared elsewhere. And another usage for Fabric is that it can be used to benchmark federated learning algorithms, as we mentioned. Like it provides heterogeneous and distributed computing. It can be used as a benchmark test bed. So yeah, okay. I hope this answered this question.
Thank you. Next question. Is there any specific application the proposed framework has been applied at DOE?
Yes, we did apply APPFL for a lot of applications. So the first one is that we apply federated learning to do detection of COVID-19 from chest X-ray images, and this is one of our biomedical application. We also use that on ECG data, electronic cardiology data to predict the age of the clients. And these two applications, we just wrote a paper that is online on structural and computational biology. These are like computational biology application, which are real world. We are working on real world private data with University of Chicago and Broad Institute at Harvard and MIT. This is in terms of biomedicine. We also use APPFL for a smart grid application. So basically, we are using some electronic usage data that are also private to predict the electronic usage, in the future. This is another area of applications that we use using real world data.
It sounds wonderful. Next question. How can we easily play with federated learning to better understand how it works?
Yeah, actually, APPFL provides several quick start tutorials on our APPFL.ai documentation. So you can just go there and go to quick start. We provide a lot of easy to run experiments you can play with to understand different components of federated learning, how it works. And with that, if you find, if federated learning could be like a good solution for the problem that you are working on, feel free to explore more on that and use APPFL to run real-world distributed training to train a more robust model.
Yep. The next question. How does Fabric ensure the security of the federated learning server to prevent connections for malicious clients?
Yeah, I would like to pass this question to my colleague Ziyang. He is an expert in this area.
Okay. Yeah. Actually, Federated provided two key features to solve these problems. The first one is private networking, the FabNet v4 and FabNet v6. The FabNet in the experiment we are using FabNet v4. These services act as a private IPv4 network, isolating the FAL servers and its client from the public network. This isolation ensures that only authorized clients with access to the Fabric testbed can connect it to a server, reducing the attack services. And the second key feature is controlled external access. Fabric allows users to manually enable and disable external access for specific IP address. For FL servers, external access can be restricted to trusted clients only, effectively blocking connections from unknown or malicious entities.
Thank you. Let me see whether we have additional questions. Okay, we got one last question here. How can the Chameleon integration with Fabric be beneficial to federated learning experiments on a large scale?
Yeah. So like Chameleon, I think the first like benefits it could provide is more compute, definitely, because Chameleon has many nodes and machines with GPU supports, so that we can easily get access to GPU machines, so we can launch more compute intensive tasks at scale. And another very interesting or important or useful feature that Chameleon integrates is that it has a very well-designed scheduling system or scheduling UI, so that you can select, like it shows when each compute machine is reserved, when it is available. So you can select a certain time, like select a certain time and find all machines available in that certain time period, and you can reserve them. So the key, what this means that you can reserve a time where you have all client machines available. This is very important because if you don't have this capability, and like suppose you have 4 HPCs, that are isolated, and you want to run a federated learning, when you get like you may submit some job on them to allocate resources. When you get resources on one node on one HPC, the other 3 nodes may be on the queue, and you cannot run federated learning experiment. You have to wait for the others to pass through their queue and get the resources. And in the worst case, right, when the other 3 resources are allocated, the first resources is gone. So that setup is very tedious without Chameleon, which connects a lot of sites together, and you can reserve them all in once. So that is another very useful features, especially for federated learning. I think these are like 2 benefits. Right? With those 2 benefits, the integration with Chameleon can help people to easily allocate resources and launch large-scale federated learning experiment for more useful and interesting federated learning experiments.
Thank you very much for that answer. Okay, so now we'll thank again our 3 speakers, Zilinghan Li, Ravi Maduri, and Ziyang. In addition to our presenter, I'll also like to acknowledge the behind-the-scenes team, our Fabric members, Chelsea Davis, Jayshree Jagannatha. They spend a lot of time to design and host these webinars. Hopefully it has been useful to the community. And next slide, please. Thank you to the audience for your participation in today's webinar. So as I mentioned, there will be a recording of this webinar. We will also email everyone with some of the resources that's available to you. The slide deck will be shared, and then there will be a Connect with Us form. I really encourage all of you to connect with Fabric team for continued questions and support for your research. Next month, we will have more webinars. Next month, we have Stitching Together Innovation with Fabric Users webinar on January 21st at 3 p.m. Eastern Time. This next webinar will focus on new users. We'll appreciate if you can forward the information to any of your friends, relevant users in your communities. And finally, if you are a Fabric user already, please consider submitting your Fabric matrix. Make sure your project information on the portal is up to date, the abstract. That will help us understand your research more, and we will promote and share your research with the community. All right. Thanks everyone again, and have a wonderful day, and Happy New Year pretty soon.